welcome everybody to this seminar. So as James mentioned, the work I will be presenting today is kind of like done by many different students. So Srivatsan, Sarah, Stephen, and of course Vaughn, who's supervising us. And I'm going to talk to you about a couple of different works that we have been doing in the recent years that are basically aimed to build tools, CAD tools, and architecture exploration tools for those next generation reconfigurable devices. So to start, I guess we should understand what do I mean by next generation reconfigurable devices. And what I mean is that the industry is kind of like shifting beyond the conventional FPGAs that we have been dealing with. So we have seen something like the Xilinx Versal that still has an FPGA fabric, but has a lot more than that, has a network on chip, hard accelerator, vector processors, and also like a standard software programmable ARM cores. And then on Intel side, we started seeing, again, more heterogeneous devices that use 2.5D integration to integrate HBM, also integrate some sort of a hard network on chip that can distribute the memory bandwidths to different locations in the fabric. And then what we are looking into in the Crossroads Center is basically something similar to what I'm showing in this figure. It's a 3D integrated device that has an FPGA fabric on top of an ASIC base die, and this ASIC base die can have all sorts of things that you would dream of. Network on chip for system level communication, hard accelerator cores, and many more. So we basically call those things reconfigurable acceleration devices, or RADs for short. And that's what I'm going to be talking about in the rest of this presentation. So really, if you look at the architecture or the design space of those RADs, you can find out that they consist of three main components. The first component is the FPGA fabric. And there are a lot of questions about the architecture of the FPGA fabric. So how would the routing look like? Should we still stick to the fine-grained bit-level routing or not? How do we architect the logic blocks? What type of hard blocks like DSPs or other types of hard blocks should we harden in this fabric? And also, what's the effect of all that on the FPGA CAD algorithms, which are the place and route algorithms that basically translate your design into hardware working on the FPGA? And then the second component are those coarse-grained accelerator blocks. And those, the way we envision those is that they're going to be like application-specific accelerators that are more beefy than things like DSP blocks that are already hardened in the FPGA. And then, again, so many questions about those blocks. So what type of functionality should we harden in those accelerators? What is the granularity of those blocks? How many of them should we put in? And then something that is typically ignored is like the programming model of those accelerators. So you have seen Xilinx put vector cores in their Versal, and then you'll have to write parts of your application in a vector software and then integrate that with the rest of your FPGA. So the programming model is really something critical that we have to think about. And then the third component is the system level interconnect, or the network on chip. Right. So what would be the specs of this network on chip? What is the abstraction presented to the user? And also very interesting interaction between having a NoC and the place and route algorithm. So what happens with the NoC placement problem, which is something that I'm going to be talking about in this presentation. So out of those three kind of like main components, the FPGA fabric component is the one that we are most familiar with. We know how to do it. We have been designing FPGA fabrics for a long time, and we have the tools to do the architecture exploration for that. So you have something like VPR, where you write RTL benchmarks or circuits, then you push them through VPR by describing an FPGA fabric architecture. You get an idea how well do those benchmark circuits operate on this candidate FPGA fabric. And this all depends on RTL benchmarks, and what you get out of it is application agnostic performance. It tells you what is the Fmax of this design and how big would this FPGA be, or how much resources would the design consume on this FPGA. And a key kind of like component of this is that you're routing wires, you're routing bit level fine-grained signals using the programmable routing of the FPGA. But then once you start thinking of the full design space of RADs, it seems that we are lacking the tools to kind of like explore the complex interactions between those components. So we need tools that capture things like routing packets instead of wires over the NoC, and also having parts of your application as hard accelerator cores, making the performance something beyond just Fmax and consumed resources. It translates to like cycles and application level performance, or application specific performance. And that's basically what we try to build over the course of the previous couple of years. So we built something that we call the RAD flow. It's an architecture exploration flow for those RADs, and it consists of three main components. The first component is what we call RAD-Sim. So this is a system simulation infrastructure. So you describe things like your application modules, your hard modules, some architecture parameters and network on chip specifications in a somewhat higher level description language than RTL. And then RAD-Sim would simulate your design and let you know how does the NoC traffic look like, what is the end-to-end application performance that you would get, and also verifies the functionality of your application when you map it to a candidate RAD. And then you can basically iterate through that by tweaking different architecture parameters and seeing what's the effect of changing those architecture features or hard accelerator core features onto your end-to-end application performance. And then the second component is what we call RAD-Gen. So with RAD-Sim, you might dream of any architecture that is not necessarily realistic to implement, right? It might be too expensive, exceeds the area budget that you have, might not run as fast as you have thought in the simulation. So we actually implement RAD-Gen, which basically takes a more detailed description now on the RTL level of your accelerator cores and some infrastructure blocks of the RAD, and then gives you the ASIC area, performance, and power results for this implementation. So RAD-Sim and RAD-Gen together can give you both sides of the equation. How fast and how well would it perform, and also how much would it cost to implement in a real device. And then the third component of the flow is kind of like an interesting interaction between RAD-Sim and the normal FPGA CAD that we know of nowadays, the place and route algorithms. And specifically, this interaction comes out of the of integrating a NoC in your device. So now the FPGA place and route tools would also need to understand that there's a NoC that exists on your device, and how things would be placed and routed over this NoC. So really, if you think about this flow in like from a very high level, you can see that the RAD-Sim is kind of like a cycle accurate architecture simulator. So if you're coming from computer architecture land, this is something that you're very familiar with. And then on the left and right side are the physical design for ASIC component and for FPGA components, which altogether comprise the flow for those heterogeneous RAD devices. So let me give you a quick glimpse on what happens inside of RAD-Sim. So RAD-Sim is developed in System-C, and the reason why we chose System-C, that it gives you varying levels of abstraction. So you can define your application in a close to like an RTL level description, or you can describe it as just a behavioral functionality coupled with some latency or performance metrics. And this basically trades off the faithfulness of your model with the productivity of how fast you want to do the architecture exploration. And then under the hood, RAD-Sim makes use of a very famous NoC simulator called BookSim to simulate all the transactions going over the NoC, but we extend BookSim beyond the vanilla one to also have bookkeeping for functionality. So we actually transfer the data over the NoC. We don't just care about performance. And also have like standardized interfaces for those NoCs, like AXI streaming or AXI memory mapped interfaces that you can hook up to. And then RAD-Sim also provides some infrastructure components and telemetry utilities that basically makes you able to probe into different parts of the system, start identifying bottlenecks and tweaking architecture parameters to solve them. So just to give you a sense of what type of inputs and outputs you would get of RAD-Sim. So on the left, there's a big table of different input parameters that you can specify. Things about like the NoC architecture, the NoC adapter architecture, the modules of your application, your hard blocks, and so on. And then on the right shows like what can you get out of RAD-Sim. So you can get statistics about, for example, what happens over the NoC, how many hops does each packet go through, and how is the latency basically broken down between different components of your NoC, and so on. And one of the features that we recently added to RAD-Sim is also the ability to simulate external interfaces, not just focused on what's going on inside the device. So for that, we actually make use of another very famous simulator for DRAM called DRAM-Sim 3, which is kind of like widely used in memory system architecture research. So we basically take DRAM-Sim, we build a RAD-Sim compatible system C wrapper around it, and make it kind of like visible to the external world over an XC memory mapped interface, which is typical in FPGA land. And then we add on top of it functional bookkeeping. So if you read and write data from the memory, you still maintain the actual contents of the data, which keeps the functional verification of aspect of RAD-Sim intact. And by doing that, you can basically hook up this to the NoC of your RAD, and then you can model applications where there are different RAD-Sim modules accessing external memory over the network connection. And just to make sure that this is like faithfully modeling what happens in real systems, we actually compare that to RTL simulation and actual hardware measurements of FPGAs that have HBM in them compared to simulating a similar device in RAD-Sim. And we actually see that the bandwidth utilization shows very similar trends. We are a little bit pessimistic for batch one reads and writes. So if you're using those in your application, we are kind of like penalizing that a little bit. And the latencies that you measure for memory transactions are kind of like similar to what's reported in prior studies about HBM systems on FPGAs. So what can we do with RAD-Sim now? We can basically model devices that look like the picture I'm showing on the right side. So devices that have a mix of an FPGA fabric, network on chip, one or more HBM stacks, DDR interfaces, and also some hard accelerator cores on the side. And this is just a variation of what you can model. You can think of this as like a monolithic device. You can think of it as 2.5D integrated or even 3D integrated, because from a simulation perspective, the implementation style doesn't matter that much. And then you can try out different NoC specifications, different architecture parameters, different accelerator cores that you want to harden, and then get a sense of how does it perform like on end-to-end applications. Okay, so this was the middle RAD-Sim component. Now let's move to the physical design component for the FPGA blocks that you have in your system. So this is kind of like the good old VPR that we know about, does placement and routing. But then, as I mentioned, there's an additional component in the system that needs to be introduced, which is the NoC. So like to start, let me quickly tell you like why hard NoCs in FPGAs is a good idea. So we all know that FPGAs are growing in capacity and the long wires on them are not scaling as well. And then modern FPGA designs are typically composed of many different IPs. And on top of that, there are a ton of high-speed external interfaces. And then you might throw in one or more ASIC chiplets, and that starts looking like a RAD device. So this really becomes a nightmare in terms of time enclosure. right? All those modules need to talk to each other, need to talk to external interfaces, need to talk to ASIC chiplets, and doing all this communication using the FPGA programmable routing is almost an impossible task. So the NoC kind of like comes in as the magic solution for this. You just focus on optimizing your individual or independent IP cores, and then you hook up those IP cores to the NoC, and then suddenly those IP cores can talk to each other and then can talk to external interfaces and other components over the NoC. You don't need to worry about things like time enclosure or bus architecture in system level interconnect. So sounds like a really good idea, and a lot of like academic studies have explored this idea from the architecture perspective, right? How much does it cost to integrate a hard NoC in your device? What are the trade-offs between hard, soft, and mixed NoCs? And we started seeing this as a reality. So both FPGAs from both Intel and Xilinx are now integrating some form of a hard NoC in their FPGAs. But then if you look at the other side of the coin, like academic FPGA CAD tools are not ready for this, right? We don't know how to optimize designs for FPGAs that include a hard NoC in them, right? So the typical place and route flow would optimize metrics like the wire length and the critical path delay of your circuit. But we also wanted to understand the notion of NoC communication. So you can also optimize things like the NoC aggregate bandwidth and the NoC communication latency while optimizing your place and route, like the place and route of your whole circuit. And this is basically our goal. So we want to enable flexible modeling of NoCs in VPR to allow us to explore architectures that incorporate hard NoCs in them. And we also want to co-optimize the NoC metrics that I talked about, the bandwidth and latency, along with the conventional circuit metrics, such as wire length and critical path delay. So first, let me quickly explain to you what the NoC placement problem is, okay? So here I have an example design that has 4 different modules. Those modules can talk to each other using normal wire connections over the programmable routing, but can also have NoC communication going on between them, which is represented by the red arrows in this figure, right? So the way to think about this is that the modules that have communication over the NoC are really connected to NoC routers. So we basically form connections between those modules and what we call logical NoC routers. And then this module would be connected using wires to the router. And then the router is thought of as a magic portal that takes data from this location, and then the data appears in another location on the device. So thinking this way, the NoC placement problem becomes, how do we map those logical routers that we have on the left side to physical NoC router locations in the device, like I'm showing on the right side? And while you're deciding on the location of those logical routers to optimize NoC metrics, you want also to keep in mind that you want to optimize the rest of the placement and routing of the circuit, as I'm showing in this figure. This flowchart shows a variation of the VPR flow that is typically used for architecture exploration of FPGAs. So it starts with a user design that is written in hardware description language, system Verilog or VHDL. It goes through a synthesis front end, and in this variation, I'm showing Quartus front end because it has good language coverage support and it's easier to deal with compared to the open source tools. The synthesis produces the tech-mapped netlist of your circuit that then gets passed to VPR along with a description of your FPGA architecture to perform the placement and routing and then give you implementation results. So in order to make this flow aware of the existence of a NoC, we need to introduce some new components. So first, the FPGA architecture needs to include a description of the network on chip that you're integrating. Then you need to let VPR know about the traffic flows or the communication going over the NoC in your design. And then you need to modify the placement engine to also optimize for the NoC metrics. So for the NoC specifications, we extend the architecture description language of VPR to include like a NoC description in your good old FPGA architecture description file that you pass to VPR. And this NoC description describes things like high-level general NoC specifications. What are the link bandwidths, latency, what are the router latencies of the NoC, and so on. And it also allows the user to flexibly describe any NoC topology that they want by saying, okay, I have this router 0 at this specific location in the FPGA grid, and it's also connected to routers 1 and 2. And this basically enables you to describe any NoC architecture that you want to integrate in your FPGA. And this is just as an example snapshot from VPR's graphical user interface. This is us trying to describe a NoC that looks like the Versal NoC with this like squished mesh topology that they integrate in Versal. So NoC specs, we can describe that. Now, we need to also describe the traffic flows of our application. So we add a new input file that you also pass to VPR that describes those traffic flows. And it basically describes things like the source and destination of each traffic flow over the NoC, what is the expected bandwidth of this traffic flow, and some other optional parameters, things like, are there some latency constraint for this traffic flow, or is there a specific priority for this traffic flow compared to other traffic flows? And then given those two new inputs, now we move on to the actual placement engine inside VPR, and how do we make use of those two inputs to optimize the NoC placement. So VPR uses simulated annealing for the placement of normal circuits, and simulated annealing typically works as I'm showing in this pseudocode. So you start with an initial placement that can be random or a little bit better than random, and then while you're optimizing your circuit, you basically pick one or more netlist primitives, and then you propose a move. And this move can be as simple as like swapping two primitives or moving a primitive to kind of like the median location of all the things it's connected to, things like that. And then once you do this move, you evaluate the cost of this new placement. And if the cost of this new placement is better than the old cost, this is a good deal, so you take it. If it's worse than the old cost, you don't completely reject it, you accept it with a specific probability. And this basically gives the hill climbing nature of simulated annealing. So in order to make the placement engine aware of the existence of the NoC and trying to optimize for it, so we need to change how the cost function is capturing those metrics. So right now, the cost function in VPR is focused on wire length and critical path delay, or proxies of those two metrics. So we also need to incorporate NoC matrix in this cost function to let the placement engine optimize for that. And this is how we do it. So as I explained, the cost function focuses on wire length and critical path delay. This is what we call the cost of the conventional cost of a circuit netlist. And then we add more metrics to it. So one metric is the aggregate bandwidth of the NoC, and the other metric is the latency of network on-chip communication. And then this parameter omega is basically how much do you focus on NoC optimization versus the conventional circuit netlist optimization. And then the aggregate bandwidth, as you can expect, it is basically giving priority to specific flows. So here T of I is a traffic flow. So the priority of this traffic flow multiplied by its aggregate bandwidths, and then you sum this up over all the traffic flows that you have. And similarly with the latency, so you also incorporate the flow priority in your equation, and then you kind of have like two independent cost terms. So the first one is kind of like focusing on, did I meet the latency constraints specified by the user? And the other component is focusing on optimizing latency in general. And then you have kind of like hyperparameters to tune, like how much do you want to focus on those two different components. Yeah, so, and basically if you notice in those different cost functions, you need to figure out things like what is the aggregate bandwidth of that specific traffic flow, or what's the latency of this traffic flow. And this really means that while you are calculating the cost, you need to perform NoC routing between the source and destination routers in order to figure out those metrics. So this part needs to be really fast because it will be called many, many times during the optimization process. And as I mentioned, there are a few hyperparameters that require some empirical tuning in order to decide the best values for them. And in order to kind of like evaluate whether the tool is basically behaving as intended, we developed some synthetic benchmarks. And those synthetic benchmarks are really simple benchmarks. So there are communication flows between a number of modules, right? That we can actually manually figure out the optimal NoC placement for those applications. So something like a chain communication patterns, like I'm showing here between modules A to G, the tool can decide to place them this way on the NoC. And this is a really terrible solution because in every hop of this chain communication, you're traversing many links and many router hops. But then an example of a good placement is basically putting all the modules to adjacent routers, and this means you hop only one NoC link every time you're moving from one module to the other. And then there can be other good placement solutions. And really the intention here is to make sure that the tool figures out those good placement solutions on its own. And in order to do that, we need to develop benchmarks that are easy to manually figure out the placement for. So we built a couple of those. One of them is the chain communication. The other one is like a star style communication where one module is communicating to all other modules. And then there are some strict latency constraint on some of those modules. And ideally the tool would decide to put the central module in a central NoC router surrounded by the modules that have critical latency constraint, and then further on the rest of the modules. And then another example is a 2D kind of like systolic array style, and the tool ideally would place this in a regular structure, as I'm showing in this figure. So now let's look at the results. So we look at the network on chip metrics, things like the aggregate bandwidths and NoC latency, and normalize the results to the optimal scenario that we can manually calculate. So if you basically use a placement engine that is not aware of the existence of the NoC, or not trying to optimize the NoC placement, you see that those metrics are kind of like a lot higher than the optimal case. But then once you enable NoC placement, which is done by the formulation that I just showed you, the tool on its own optimizes those NoC metrics and figures out solutions that are very close to the optimal solution that we are waiting for or hoping for. On the other hand, like while the tool is optimizing those NoC metrics, it's also optimizing the rest of the circuit metrics, things like the critical path delay and wire length. So we want to make sure that adding this NoC optimization component did not mess up the rest of the circuit metrics. And this is basically showing the wire length and critical path delay normalized to without incorporating NoC placement. And you can see that it has very minimal effect on those metrics. So from those results, we make sure that the tool is behaving as we intended to behave, right? It's optimizing NoC metrics well, and it's not messing up the circuit metrics. So now we need to try and test bigger designs, bigger and more realistic designs. But then it becomes a little bit problematic because those traffic flows that I talked about, like describing the traffic patterns between modules, are easy to write if you have a simple application, right? For those chain or 2D connections or star connection, it's easy to write this traffic flow file. But what about a complex, large application design? And here, where it kicks in the nice interaction between that and RAD-Sim that I was talking about earlier in the talk. So RAD-Sim has the ability to simulate the whole end-to-end application, incorporating NoC communication in it. So really, if you're able to simulate the application in RAD-Sim, RAD-Sim can write the traffic flows file for you without you needing to go in and manually figure out what are the traffic flows. Yeah, so we use RAD-Sim to simulate the application and generate the NoC traffic flows, and then we pass it on to VPR to optimize the NoC placement. And the example that we experiment with is basically multi-layer perceptron acceleration. So it's streaming style accelerator for neural networks. And the way this example design is composed is so you have many matrix vector multiplication engines that basically can compute the multi-layer perceptron layers, and they are communicating between each other over the NoC. And just to give you a sense of how big this example design would be, so each matrix vector multiplication engine is tens of thousands of logic elements, hundreds of DSP blocks and DRAMs, and each one of the example designs that we play with is 6 to 11 of those matrix vector multiplication engines in the same design. So really, this is a big FPGA application. I think when I tried to fit this in a Stratix 4 device, it wasn't enough, and it was filling a good portion of a Stratix 10 device. So looking at the results, by experimenting with like 4 different multi-layer perceptron designs, we can see that VPR, the NoC-aware VPR, is kind of like optimizing the NoC metrics well. So it achieves 2 times lower aggregate bandwidths and 1.6 times lower latency than when the tool is not aware of the existence of the NoC, which is something that we expect. And then on the other hand, it's also not affecting the frequency or the routed wire length of those applications. And since we incorporate a new optimization stage in the flow, or like optimization target in the flow, this increases the placement time by about 17% on average. So now you're optimizing for the circuit and also the NoC metrics. And this figure is basically showing an example design with those matrix vector engines for different layers of the multi-layer perceptron colored with different colors, and showing that the initial random placement that we start with is basically all over the place. The modules that are talking to each other, highlighted by the arrows, are kind of like scrambled around. It's not ideal for NoC communication. And once we pass this to VPR to optimize the NoC placement, the solution that we get out of that is a lot more regular and a lot more friendly for NoC communication, with the traffic flows being more local and basically between adjacent modules. Yeah, so I will probably skip over this for the sake of time, but we also explore the trade-offs between some like a flow similar to what I described, where the placement engine is co-optimizing the NoC and the circuit metrics, versus another flow that would look only at the NoC metrics, optimize that, lock the NoC placement down, and then optimize the circuit metrics. And then we figure out that the co-optimization approach works a lot better in the example cases that we try. Okay, so now I covered kind of the simulation infrastructure in the middle, and then the link to the conventional FPGA CAD tools. Now let's talk about the last component of the flow, which is the ASIC design, like the physical design for ASIC components. So we built this tool called RAD-Gen, and the goal of RAD-Gen is basically to provide users with kind of like a press play flow that gives them an estimate for ASIC implementation cost, frequency, and power, starting from an RTL description. And we're trying to do that to abstract away all the subtleties of setting up your own ASIC flows, figuring out the right settings to use, and so on. So basically, the inputs that you give to RAD-Gen are a configuration file that basically specifies the settings for some of the high-level settings for the ASIC flow, and also a process design kit or a PDK that you want to use. You also give it the RTL files for your blocks that you want to evaluate, and some of the parameters that you want to sweep. So for example, if I want to evaluate the cost of NoC routers, right, there are parameters such as how many virtual channels do I have in the NoC router, what is the NoC link width, what are the virtual channel buffer sizes, and so on. So those are all parameterized in the RTL design. You just give those parameters to RAD-Gen, and then RAD-Gen will sweep different options and give you the implementation costs of all those options. And then internally, RAD-Gen is technically a bunch of scripts. So some scripts that prepare the directories and the configurations for all the ASIC runs, figure out what type of SRAMs do you have in your designs. And then internally, we build an SRAM mapper, and the whole target of this SRAM mapper is basically if you have a PDK that has a few SRAM macros in it, and then you have SRAMs in your design that are of different sizes or dimensions, it tries to map those dimensions to those macros and stitch them together using external logic in order to be able to give a pessimistic estimate of this SRAM cost. And then we make use of Hammer, which is a tool from the UC Berkeley chipyard framework that basically provides a modular ASIC flow where you can swap in and out different synthesis, place and route, and static timing analysis tools very easily. And at the end, we have like some post-processing scripts that prepare the final results and also incorporate things like scaling GDS files in some PDKs that try to trick the tool licenses by having a GDS that is kind of like bloated up. So anyway, the post-processing script kind of like prepares the final results and gives you a report. Here are different options that we tried for the parameters you want to sweep. Here are the cost for those components in order to get a sense of what's realistic to embed in your RAD architecture. So given this RAD-Gen infrastructure, now we are ready to evaluate things like NoC routers and accelerator cores that are a candidate for integration in our RAD device. Again, going back to this picture that we are trying to model in the tool flow that we have. So in order to basically take those tools for a spin, we do a case study on one of the most interesting deep learning applications nowadays. Those are deep learning recommendation models, or DLRMs. So if you're using any of the products I'm showing in the top right corner, Netflix, Instagram, TikTok, YouTube, or doing online shopping, 99% of the time you're using some variation of a DLRM. And the use of the DLRM is basically to recommend what to watch next or what to buy based on your previous patterns of use and also what other people think about those things. And the way deep learning recommendation models work is that they get as an input some dense features that represent numerical data, things like, for example, the user age or other numerical metrics, and some sparse features that are either one or multi-hot vectors that basically say, for example, things like what's the user country, or what products did you buy before out of a specific list of products, right? So those are one-hot vectors typically. Then the dense features go through multi-layer perceptron, which is shown here as the bottom multi-layer perceptron, to map the input dense feature to another dense space. And then those sparse features, the one-hot vectors, the indices of the entries that are set to 1 are used as memory addresses that you go read from those embedding tables that I'm showing here. So for each one of the sparse features, you read an embedding from the embedding tables, and then you get a dense representation on the output of the embedding table. Then you do some form of feature interaction, which can be as simple as a concatenation of the MOP output and the embedding table outputs, or you can do things like weighted sums or element-wise operations if those outputs are all of the same size. And then this kind of like combined output is then fed into another multi-layer perceptron to produce the final prediction, whether you would like to buy this product or not, for example. So we take this application, we build an FPGA accelerator for it. So you can see we have a multi-layer perceptor and accelerator that accelerates those MLP component. We have an embedding lookup module that basically takes the sparse features and looks them up from external memories that can be HBMs or DDRs. And by the way, the reason why those are on external memory is that those are usually huge. They cannot fit on chip memory. And then the results coming back from the external memories go to a feature interaction module to go to the multi-layer perceptron and then produce the prediction. Okay, so we built the FPGA accelerator for that. And then we basically try to evaluate it on a conventional FPGAs. So what I'm showing here is the chip planar view of a Stratix 10 device. And this basically, so yeah, maybe a little bit of background. So Intel, for some reason, decided to put the HBM stacks on opposite sides of the chip rather than on the same side of the chip to be able to distribute that more easily to different parts of the fabric. But an application like DLRM, where you're reading from all HBM channels and kind of like bringing them together to do feature interaction, is basically getting penalized by that. So if you see now the DDR interfaces in green and the HBM interfaces in yellow are kind of like dragged along to the middle of the chip where the feature interaction is happening. So this results in like very long critical path delays for those connections that need to be very carefully tuned in order to make this viable accelerator. Then we evaluate what if we have a NoC instead of just doing all this routing using the programmable routing. So I'm showing here logic logged regions that are kind of like reserving locations of the NoC routers. So now you can see everything is more localized. The HBM interfaces are localized. The feature interaction module doesn't have to be scattered around. Everything looks a lot better. But then a lot of the soft logic is still used by the matrix vector multipliers or the MLP accelerator. So we try a third option, which is what if we move to a RAD instead of an FPGA, right? So we dedicate about 12% of the fabric area, which corresponds to a column of clock regions, to basically harden matrix vector multiplication engines. And the communication between the rest of the modules and those engines can happen only over the NoC, which mimics a RAD device similar to what I was explaining at the beginning. So now how would the tools that I described we built help evaluate such RAD architecture? Okay, so we can start by evaluating the application performance using RAD-Sim. So we built the application in RAD-Sim and we use two basically DLRMs from Alibaba that are basically mimicking realistic DLRMs that they deploy in their data centers. And then in RAD-Sim, it's very easy to explore different scenarios, right? So we basically experiment with different matrix vector multiplication core sizes. So a small core, a medium core, and a big core. Those are the cores that are hardened on the side of the RAD. And we also sweep parameters like what if we have a wider NoC, or what if we have a deeper virtual channel buffer for the NoC, and so on. And then we can basically, RAD-Sim can report what's the effect of those different architecture options on the end-to-end latency of DLRM inference, and also how many inferences you can do per second. So you can basically see, as expected, if you harden a bigger matrix vector multiplication engine, you start getting higher throughput and lower latency because you're throwing more compute at the problem. It seems that if you make your NoC wider, you start affecting performance. So jumping from a medium width NoC to a very wide NoC was like 328 bits per link. You can start affecting the performance considerably, especially when you're dealing with large compute engines. That's basically saying if you're throwing more compute, you also need to throw more communication bandwidths to keep this compute fed all the time. And then it seems from all the evaluation points that we are showing here is that the virtual channel buffer size does not have that much of an impact on performance, okay? So by doing that, RAD-Sim kind of like gives you an idea what architecture metrics are important versus not important for your target applications, right? So in this case, we would like eventually choose the smaller virtual channel buffer size to pay less cost for this. But other than that, RAD-Sim can also show you cases where the application itself becomes problematic. So in this case where the bars are missing, this is basically the most compute-intensive accelerator cores, so the biggest MVM engines, along with the narrowest possible NoC that we can implement, okay? And this basically turns out that if you choose this combination of architecture parameters, the whole application deadlocks, right? So it's not a good option. And then if we are only looking at this side of the equation, of course, I would choose the option that gives me the highest performance, right? So the biggest MVM engines and the widest NoC that achieves the best performance, right? But we really don't know if this is a realistic design choice or not. So now we go to the other part of the flow, which is RAD-Gen, and start evaluating the cost of implementing those options. And basically, RAD-Gen can give you the estimate of the area of each of those different components. How much do you have dedicated for SRAMs versus the dot product engines and the multi-layer or the MVM engines, and then how expensive would be the NoC routers. So it turns out that the biggest MVM engine is unrealistic because it exceeds the area budget that we specified at the beginning to be 12%. And in addition to the ASIC cost of the accelerator cores, it also gives you an idea of how much of the fabric are you giving up to integrate those hard NoC routers compared to a conventional FPGA. So yeah, by looking at this cost, you can start basically sorting out those design options. And then the other extreme is kind of like underutilizing the area for no reason. So you can exclude those options. And then virtual channel buffer size doesn't matter, or the highest NoC width does not improve performance that much compared to the lower option. So it seems that the sweet spot of our architecture is somewhere in this like green rectangle. So this is kind of like the things that you can do with the tools that we have developed. I'm going to skip over this for time, but this is showing the potential performance of those RAD architectures on DLRMs. So you can see it's like an order of magnitude better than current FPGAs and about 2 orders of magnitude better if you have a high batch CPU implementation. Yeah, so what are the key takeaways of what I've talked about? So whatever is beyond FPGAs, which we call RADs, is here. So we have seen products that start going in this direction, and we need the tools to explore the huge architecture design space of those architectures. And I've shown you 3 different tools that we have developed for that. So a cycle accurate simulator, which is RAD-Sim. You can basically tweak architecture parameters and see the effect on end-to-end performance of your application. Then how does that interact with the FPGA CAD tools in the NoC placement problem? And I've showed you that we made VPR NoC-aware. The third component is basically evaluating the implementation cost of the ASIC components you want to harden by using RAD-Gen. And this gives the other side of the coin along with RAD-Sim. So yeah, thanks for your attention. If you're curious to know more about anything that I've talked about, all the papers are in this webpage, and all the tools that I've talked about are open source. So you can check the RAD flow, and the NoC-aware VPR is already pushed to the master branch. So yeah, those QR codes will take you there.